So Laplace's equation in 3 dimensions is d squared by dx squared of the potential plus d squared by dy squared of the potential plus d squared by dz squared of the potential all has to equal 0. Okay, and I can't give you a good example of this. There's nothing really intuitive in your typical life that really helps you see what is really going on here. It's kind of hard to extrapolate the rubber sheet on top of you know, that odd shape I gave you in the last lecture to 3 dimensions. But the two facts are consistent. One, the potential at a point is the average of the neighbors. Two, that there is no local max or min. Okay, so the extremes are going to occur on the boundary conditions for whatever solution you find. So proving one, we're going to use the example that you've seen about 20 million times now. So we have a sphere centered on the origin, okay, and then we have up here a point charge Q, okay, and what we're trying to do is we're trying to calculate what the potential is at the center of the origin based on what the potential is at each part of that sphere. Okay, so really quickly, there's a radius r here. This is the height r, which is the distance from the origin of the sphere. And so let's write things out. So we expect so the potential at the origin should just be 1 over 4 pi epsilon naught q over r. So that's the answer we're looking for. So let's walk through this integral. Try to save some paper here. So we start out with the V average equals the surface area of the sphere, 1 over 4 pi r squared, times the integral of the potential for each of the points on that sphere. Okay, so writing that out in longhand, we have 1 over 4 pi r squared times the integral of the sphere. The potential is at any point along there is 1 over 4 pi epsilon naught times the charge divided by the distance from a point on that sphere to the charge, and that distance is given by the law of cosines as the square root of r squared plus capital R squared minus 2r capital R cos theta. Okay, there we go. Okay, we're going to need that extra space there. And the dA in spherical coordinates is the radius squared sine theta d theta d phi. Okay. The next step we're going to do is we're going to bring out some terms. That's the surface area of the sphere. And then we're going to bring out 1 over 4 pi epsilon naught. And we can bring out q because that's constant. And we're going to have the integral of d phi from 0 to 2 pi. And the integral from 0 to pi of theta. So we're going to have sine theta d theta all over the square root of r squared plus r squared minus 2r r cos theta. And we've actually solved an integral like this before, so I'm going to walk through how you do that rather quickly. So we're going to choose u to be equal to the square root of that stuff on the inside. So r squared plus r squared minus 2r r cos theta. And so du is going to be equal to the derivative of the outside, which is 1/2 1 over u, times the derivative of the inside. So that's, oh gosh, is there a negative sign there? There should be. Yes? No? Oh, here we go. Okay, so we have minus 2r, and the derivative of cosine theta would be negative sine theta. This is multiplied d theta. So those negative signs do cancel. So we have 1 over 2u. Oh, this cancels, that cancels. So we get rr sine theta d theta. And not to get ahead of myself, but where did my r squared go? My r squared disappeared. There he is. He's back. So I want to have this. I'm going to multiply by r, divide by r, and I get u d theta, right? And that looks like an easy integral to solve, particularly when you see that this is the inside of that integral. So let's continue working along here. Q, integral from 0 to 2 pi of phi is 2 pi. And then we have r du over r. So r and r can be pulled out. No, little r can't be. So we have r, let's pull out the r. So we have du over r u. No, r can be pulled out. It's a constant because we're not varying r. Okay? du over u. So I pulled out this r, and they're right here right now. And that becomes a really easy integral to solve. And the integral of there is just, let's see, is it one? No. No, I don't have that u. It's just du. So it becomes u. Evaluated. Well, when theta is 0, then u becomes, let's see, cosine theta is 1, so it becomes the square root of r minus r squared. And when theta is pi, it becomes the square root of r plus r squared. Okay, completing the square in there. And so that equals, let's start canceling some terms out here. Let me pull out a different color marker. Okay, so 2 pi, boom, boom, leaving a 2. R, boom, boom. Where'd my r squared go? Oh, that's right, it's just r. Okay, we have an r in the bottom, we have q over r. We have 1 over r, 1 over 4 pi epsilon naught, 1 half r. Okay, so this inside bit here, so we have 1 over 4 pi epsilon naught q over 2r r, and then we have the square root of this. Now I forgot to tell you this, but the square root is equal to, the square root of a square is equal to the absolute value, almost by definition. Okay, so when we plug this all in, we get r plus r minus r minus r. Okay, now as long as r is bigger than big R, little r is bigger than big R, this is going to be positive on the inside. So it's going to be equal to the positive of this. And the same for this. This is always going to be positive unless we start going negative, which we're not. So it becomes r plus r minus r plus r, because we distribute that minus sign. And so these two cancel, and we have 2r. Okay? And I did run out of paper. Oh well. So wrapping things up here, we get the potential of the average Q divided by the 2r cancels the 2r, so we have just an r in the bottom. And lo and behold, that's exactly what we expected it to be. And I wasted a whole piece of paper just to write the answer. So there we go. It turns out the same. So I didn't really prove that it worked, that this is true everywhere. I just proved that it works. And if you want a more exhaustive proof, you can probably think about it for a while and understand why the average has to be the way it is. So fortunately, time doesn't provide me to give more complete proof of this. And of course, we want to move on to learn more about electrodynamics. So anyway, I hope you enjoyed this film. Take care.